What if gravity could bend light, creating cosmic mirages? This incredible phenomenon, known as gravitational lensing, is a direct consequence of Albert Einstein's revolutionary theory of general relativity. Published in 1915, general relativity fundamentally reshaped our understanding of gravity, moving beyond Isaac Newton's description of gravity as an innate force of attraction between objects. Einstein's groundbreaking insight was to unify space and time into a single, four-dimensional entity called spacetime. This fabric of space-time is not a rigid, unchanging stage upon which cosmic events unfold. Instead, it's a dynamic, flexible medium that can be pushed, pulled, stretched, and warped by the presence of matter and energy. Think of it like a stretched rubber sheet. If you place a bowling ball in the center, it creates a dip or a curve in the sheet. Now, if you roll a marble across the sheet, it won't travel in a straight line. It will curve inward towards the bowling ball, not because the bowling ball is attracting it with a mysterious force, but because the sheet itself has been deformed. This analogy, while helpful, has its limitations. Space-time isn't a physical fabric in the literal sense, nor is it made of threads. It's a mathematical framework, a four-dimensional differentiable manifold equipped with a Lorentzian metric that defines distances, time intervals, and how objects move. But the core idea remains: massive objects, like stars, planets, and especially galaxy clusters, create significant distortions in this fabric of spacetime. In Einstein's view, what we perceive as gravity is not a force pulling objects together, but rather a manifestation of this curvature of spacetime. Objects, including light, simply follow the straightest possible path through this curved spacetime. For instance, the Earth orbits the Sun not because of a direct pulling force, but because the Sun's immense mass warps the spacetime around it, and the Earth follows this curved path. This means that even light, which we typically think of as traveling in straight lines, must follow the curvature of spacetime when it passes near a massive object. This concept was a radical departure from Newtonian physics. Newton's laws assumed gravity was an innate force acting over a distance, and that space and time were absolute and independent. Einstein's special theory of relativity, published a decade earlier, had already established that space and time are inextricably connected and relative to the observer's motion, with the speed of light being constant for all observers. General relativity then extended this to include gravity, revealing that gravity and acceleration are fundamentally indistinguishable. This principle of equivalence was a key stepping stone for Einstein, leading him to the realization that gravity is not a force, but a property of spacetime itself. The implications of spacetime curvature are profound. It means that time itself can be affected by gravity, running slower in stronger gravitational fields, a phenomenon known as time dilation. This effect is so precise that it must be accounted for in GPS satellites to ensure accurate positioning. But for our purposes, the most visually striking consequence of spacetime's curvature is its effect on light. When light encounters a gravity well, or a significant distortion in spacetime caused by a massive object, its path is bent. This bending of light by gravity is precisely what we call gravitational lensing. It's a cosmic phenomenon where massive celestial bodies act like colossal lenses, focusing and distorting the light from objects located behind them. This bending of light by gravity is precisely what we call gravitational lensing. It's a cosmic phenomenon where massive celestial bodies act like colossal lenses, focusing and distorting the light from objects located behind them. But how exactly does this cosmic magnifying glass work? At its heart, gravitational lensing is a direct consequence of Einstein's theory of general relativity. This revolutionary theory posits that space and time are not separate entities, but rather interwoven into a single, flexible fabric called spacetime. Massive objects, like galaxies and galaxy clusters, warp, or curve this fabric around them, much like a bowling ball placed on a stretched rubber sheet. Now, imagine light, which we typically think of as traveling in straight lines. In the context of general relativity, light always follows the straightest possible path through spacetime. However, if spacetime itself is curved, then the path light takes will also appear curved to us, the observers. It's not that gravity directly pulls on the photons of light in the same way it pulls on objects with mass. Instead, the photons are simply following the curvature of the spacetime fabric that the massive object has created. For gravitational lensing to be observable, a significant amount of mass is required to sufficiently bend spacetime. This is why we typically see gravitational lensing effects on cosmic scales, involving objects as massive as entire galaxies or even clusters of galaxies. These immense structures act as the lenses in the universe. When light from a distant source, perhaps a star, a quasar, or a faraway galaxy, passes by one of these massive gravitational lenses on its journey to Earth, its path is deflected. The result of this deflection can be quite spectacular. Just like an optical lens, a gravitational lens can magnify, brighten, and distort the image of the background object. This magnification is incredibly valuable to astronomers, allowing them to observe objects that would otherwise be too faint and distant to be seen, even with our most powerful telescopes like the Hubble and James Webb Space Telescopes. It's like having a natural, universe-sized telescope that extends our vision far beyond what our technology alone could achieve. Beyond simple magnification, gravitational lensing can also produce a variety of other fascinating effects. Depending on the alignment of the source, the lens, and the observer, the light from a single background object can be bent in such a way that it creates multiple images of that same object. These multiple images often appear as distorted arcs or streaks of light around the lensing galaxy or cluster. In some rare and almost perfect alignments, the light can be stretched into a nearly complete circle, a phenomenon famously known as an Einstein ring. The degree to which light is bent depends directly on the mass of the lensing object. The more massive the object, the greater the curvature of spacetime, and thus the more pronounced the bending of light. By carefully studying the distortions and magnifications produced by gravitational lenses, astronomers can actually infer the mass of the lensing object, even if that mass is invisible to us. This makes gravitational lensing an indispensable tool for understanding the distribution of matter in the universe. It's a cosmic detective, revealing the presence of unseen mass through its gravitational influence on light. Gravitational lensing manifests in various forms, each offering unique insights into the cosmos. These are broadly categorized into strong lensing, weak lensing, and microlensing, distinguished by the mass of the lensing object and the degree of distortion it imparts on the background light. Strong gravitational lensing occurs when a massive object, such as a galaxy or a galaxy cluster, perfectly or near perfectly aligns with a distant background source. This precise alignment, coupled with a sufficiently large mass in the foreground, leads to dramatic and easily observable effects. The light from the background source is significantly bent, often resulting in multiple images, arcs, or even complete rings of light. One of the most striking examples of strong lensing is the Einstein ring. This phenomenon occurs when the source, lens, and observer are in almost perfect alignment, causing the light from the background object to be distorted into a luminous circle around the foreground lensing object. While theoretically a perfect circle, observed Einstein rings often appear as ovals or partial arcs due to imperfect alignment. These celestial bullseyes are rare, requiring a precise cosmic arrangement. Scientists have used the Hubble Space Telescope to discover several Einstein rings, with one notable example being a double ring formed by the light of three galaxies at different distances, 3, 6, and 11 billion light-years. Such discoveries provide valuable data for understanding dark matter distribution, dark energy, and the curvature of the universe. Another fascinating outcome of strong lensing is the Einstein cross, where the light from a distant quasar is split into four distinct images arranged in a cross-like pattern around a foreground galaxy. The first Einstein cross, known as Q0957+561, was discovered in 1979, and it took careful observation to confirm that the two bright objects were, in fact, multiple images of the same quasar. The quasar in Q0957+561 is approximately 8 billion light-years away, while the lensing galaxy is about 400 million light-years distant. The elongated shape of the lensing galaxy and the quasar being slightly off-center contribute to the cross formation rather than a ring. These cosmic mirages are powerful tools for studying the properties of distant galaxies and quasars, as well as the distribution of dark matter within the lensing galaxy. Beyond these distinct multiple images, strong lensing also produces giant arcs, which are stretched and magnified images of background galaxies. These arcs are particularly common when galaxy clusters act as lenses, their immense gravitational fields distorting the light of numerous background galaxies. By studying these arcs, astronomers can accurately measure the total mass, including dark matter, of galaxies and clusters at cosmological distances. They also allow for the study of very distant and young galaxies that would otherwise be too faint to observe, effectively acting as natural telescopes. In contrast to the dramatic effects of strong lensing, weak gravitational lensing involves less massive foreground objects or less precise alignments. Here, the distortions of background galaxies are subtle and cannot be easily discerned in individual images. Instead, weak lensing is detected statistically by observing the systematic alignment and slight stretching of many background galaxies around a foreground mass. Imagine countless faint, distant galaxies, intrinsically oriented randomly in the sky. When their light passes through the weak gravitational field of an intervening mass, they are all subtly stretched in a coherent direction, tangential to the lensing mass. This collective, subtle distortion, known as shear, provides a powerful way to map the distribution of both visible and dark matter on large scales. Weak lensing is particularly valuable for studying the distribution of dark matter in galaxy clusters and the large-scale structure of the universe, as it doesn't rely on assumptions about the composition or dynamical state of the lensing mass. The distortions, though small, are directly related to the gravitational potential of the foreground mass. By analyzing the ellipticities of millions of galaxies across vast regions of the sky, scientists can statistically detect this shear signal and reconstruct maps of the underlying mass distribution, revealing the invisible scaffolding of dark matter that pervades the cosmos. This technique is so sensitive that it can even detect the gravitational influence of the cosmic web, the filamentary structure of matter that connects galaxy clusters. Finally, we come to microlensing, a phenomenon caused by relatively small lensing objects, typically individual stars or even planets. In microlensing events, the alignment between the source, lens, and observer is often extremely precise. But because the lensing object is much less massive than a galaxy or cluster, the light deflection is too small to produce multiple, resolvable images or noticeable distortions in shape. For instance, observations of galaxy clusters like the Bullet Cluster 1E0657-56 have provided some of the most direct evidence for dark matter. In this colossal cosmic collision, hot gas, which represents the normal matter, was slowed down by the impact and glows in X-rays, shown in pink in composite images. However, the gravitational lensing analysis reveals that the majority of the mass, depicted in blue, passed through the collision largely unimpeded and is distributed differently from the hot gas. This separation of normal and dark matter during the collision is strong evidence that dark matter interacts primarily through gravity and very little, if at all, with itself or with normal matter. Weak gravitational lensing, in particular, is an incredibly promising technique for mapping the distribution of dark matter on larger scales. While strong lensing produces dramatic arcs and multiple images, weak lensing causes subtle distortions in the shapes of background galaxies. By statistically analyzing these minute distortions across vast regions of the sky, astronomers can infer the underlying distribution of dark matter, even in areas where there isn't a concentrated galaxy cluster acting as a strong lens. This method is crucial for understanding how dark matter halos are structured around individual galaxies and how the cosmic web of dark matter filaments has evolved over billions of years. Projects like the Euclid mission are specifically designed to use weak gravitational lensing to investigate the nature of dark energy and dark matter, promising deeper insights into the universe's expansion. Beyond the mysteries of dark matter, gravitational lensing, especially microlensing, has revolutionized our ability to detect exoplanets, planets orbiting stars beyond our solar system. Traditional methods for finding exoplanets, like the transit method or radial velocity, are often biased towards finding larger planets close to their host stars. However, microlensing offers a distinct advantage. It can detect planets across a wide range of masses, from gas giants to Earth-mass worlds, and at greater distances from their host stars, including those far from Earth and even free-floating planets not bound to any star. The principle behind microlensing for exoplanet detection is ingeniously simple. When a foreground star, acting as a lens, passes almost perfectly in front of a more distant background star, the foreground star's gravity magnifies the light from the background star, causing a temporary brightening event. If the foreground star hosts a planet, the planet's own gravitational field will create an additional, smaller spike or dip in this brightening curve. By carefully analyzing the shape and duration of these light curve anomalies, astronomers can infer the presence of a planet, as well as estimate its mass and orbital distance from its host star. The first exoplanet discovered using microlensing was in 2004, and since then, this technique has led to the discovery of hundreds of exoplanets. Notable discoveries include a cool planet with 5.5 Earth masses in 2006, and in 2017, an extremely massive exoplanet or brown dwarf about 13.4 times the mass of Jupiter. In 2020, astronomers even reported the detection of an Earth-mass rogue planet, unbound by any star and free-floating in the Milky Way galaxy, a discovery made possible solely through microlensing. Microlensing is particularly sensitive to planets located between roughly 0.5 and 10 AU from their host stars, a region that includes the snow line, where planetary formation is thought to be most efficient. This makes it an invaluable tool for understanding the demographics of planetary systems, complementing the discoveries made by missions like Kepler. Future missions, such as the Nancy Grace Roman Space Telescope, are designed to utilize microlensing to discover thousands of new exoplanets, further expanding our census of planetary systems in the galaxy. Gravitational lensing also holds immense potential for future exoplanet characterization. While current microlensing detections often don't allow for immediate follow-up observations to study atmospheric or interior properties, the precision offered by future observatories could change this. Researchers are even exploring the possibility of using the Sun's own gravitational field as a colossal lens to achieve unprecedented imaging precision of distant exoplanets. This solar gravitational lens could potentially allow astronomers to reconstruct surface features on exoplanets, offering detailed insights into their atmospheres, cloud distributions, and even the possibility of detecting signs of life. The potential of gravitational lensing in unraveling cosmic mysteries is truly astounding, and the future promises an explosion of new discoveries. The concept of a solar gravitational lens, SGL, telescope, for instance, holds the key to achieving unprecedented imaging precision of distant exoplanets. This innovative approach could allow astronomers to reconstruct surface features on exoplanets with resolutions as fine as 25 kilometers for an exoearth 30 parsecs away, offering detailed insights into their atmospheres, cloud distributions, and even the tantalizing possibility of detecting signs of life. Imagine being able to map continents and oceans on worlds light years away, reaching the focal region of the Sun's gravitational lens, which begins around 547 to 550 AU from the Sun, is a significant engineering challenge. For context, Voyager 1, the most distant human-made object, is currently just under 150 AU from the Sun and took decades to get there. However, ambitious plans are underway, utilizing advanced propulsion methods like solar sails to send spacecraft to this distant frontier within a few decades. Once a probe reaches this region, it wouldn't need to stop. The solar gravitational lens creates a focal line, meaning the spacecraft can continue to travel along it, continuously collecting data and refining images as it goes. This offers the unique advantage of sustained observation, potentially allowing us to monitor exoplanets for seasonal changes, much like a virtual orbiter. The SGL's incredible amplification factor, up to 100 billion times at 1 micrometer wavelength, and extreme angular resolution make it an unparalleled tool for direct, high-resolution imaging and spectroscopy of Earth-like exoplanets. Beyond exoplanets, gravitational lensing is poised to revolutionize our understanding of the universe's fundamental components. Dark matter, which constitutes about 26% of the universe but remains invisible to telescopes, is a prime target. Gravitational lensing is one of the most powerful tools for mapping its distribution because it reveals the gravitational effects of this unseen matter on light. Upcoming missions like the European Space Agency's Euclid, launched in 2023, are specifically designed to use weak gravitational lensing to investigate the nature of both dark matter and dark energy. The Nancy Grace Roman Space Telescope, set to begin science operations in 2027, will also provide vast surveys of the cosmos, identifying over 160,000 gravitational lenses, including hundreds suitable for detailed study of dark matter distribution. Gravitational lensing also offers a unique window into the early universe. By magnifying light from extremely distant galaxies, it allows us to observe objects that would otherwise be too faint or too far away to be seen, essentially peering back in time to when the universe was much younger. This enables astronomers to study the formation and evolution of the first galaxies, providing crucial insights into how the universe developed after the Big Bang. For example, gravitational lensing has already allowed astronomers to examine a distant galaxy resembling the Milky Way as it appeared over 12 billion years ago, offering new insights into early galaxy formation. The integration of artificial intelligence, AI, and machine learning is rapidly accelerating the pace of discovery in gravitational lensing. Analyzing the vast amounts of data generated by modern telescopes to identify lensing events is a monumental task. AI algorithms, once trained, can analyze new lenses almost instantaneously with a precision comparable to traditional methods, and even determine the uncertainties of their analyses. This capability is crucial for handling the data floods from next-generation observatories. Projects like Space Warps, developed in collaboration with the European Space Agency and the Euclid mission, are already using AI alongside human citizen scientists to identify strong gravitational lenses in deep space images, with thousands more expected to be discovered. This hybrid approach is proving highly effective in managing the scale and complexity of astronomical data. The future of gravitational lensing extends to even more exotic phenomena. Multi-messenger gravitational lensing, which combines observations from various cosmic messengers like gravitational waves, neutrinos, and electromagnetic radiation, is expected to deliver breakthroughs in fundamental physics and cosmology. Lensed gravitational waves, for instance, could provide powerful probes of dark matter, the Hubble constant, and other cosmological parameters. The existence of primordial black holes, a potential candidate for dark matter, can also be constrained through microlensing and by analyzing lensed gravitational wave signals from binary black hole mergers. Next-generation telescopes will be instrumental in these endeavors. Observatories like the Vera C. Rubin Observatory and the Nancy Grace Roman Space Telescope will significantly increase the number of observed gravitational lenses, providing unprecedented data for analysis. The James Webb Space Telescope, while not a survey telescope, offers high-resolution follow-up capabilities for strong lensing systems, revealing intricate details. Even the Event Horizon Telescope, known for imaging black holes, utilizes gravitational lensing to observe photons bending around the event horizon, and future iterations promise even better resolution, allowing us to watch the evolution of black holes over time. In essence, gravitational lensing is not just a fascinating consequence of Einstein's theory of relativity. It's a dynamic and evolving field at the forefront of astrophysics. With advancements in telescope technology, the power of AI, and innovative mission concepts like the solar gravitational lens, we are on the cusp of a new era of cosmic exploration, ready to unveil the universe's deepest secrets, from the elusive nature of dark matter and dark energy to the detailed landscapes of distant exoplanets and the very first moments of cosmic history.